Hey everyone, welcome to today's Explainer. I'm Dr. Chem, and we are treating today's session like a virtual laboratory experiment. We're going to be diving right into the conductivity measurement of electrolytes. Basically, we're exploring exactly how we measure the electrical conductivity of different solutions and figuring out how, exactly, ions allow electricity to just flow right through liquids. It's a fundamental physical property, but seeing how scientists and engineers actually capture these measurements is absolutely fascinating. So let's get into it. Okay, here's our quick roadmap for the lab. First, we'll look at ions in motion. Then, compare strong versus weak electrolytes. After that, we'll tackle the non-aqueous challenge, followed by measuring conductivity using AC and DC. Then, we'll look at setting the gold standard and wrap it all up with modern sensors and applications. Starting things off with part 1, ions in motion, the microscopic tug of war. Let's zoom way in and look at this from the perspective of a single ion to really understand the invisible forces at play here. Imagine a tiny charged particle just adrift in a vast molecular sea of solvent. When we apply an electric field to this, we're basically giving that ion a push. But it's definitely not a frictionless glide. The ion has to constantly shoulder its way through a thicket of solvent molecules. It's a literal tug of war between the electric push driving it forward and the viscous drag of the liquid holding it back. The steady speed it eventually reaches when those two forces balance out, well, that's what ultimately determines the solution's conductivity. Now, here's a question for you. What happens when we scale things up? Like, if we just keep adding more ions into the mix, increasing the concentration, does the conductivity just keep going up in a straight line? Well, it's not that simple. It really depends on what exactly we're dissolving. Which brings us to part 2, strong versus weak electrolytes, the concentration effect. Comparing these different behaviors is kind of the core objective of any fundamental conductivity experiment. When you dissolve electrolytes in water, they break apart into ions, but they definitely don't all do it the same way. Strong electrolytes, things like sodium chloride or hydrochloric acid, they dissociate 100%. They flood the solution with ions, giving us super high conductivity. But get this, at really high concentrations, their conductivity actually drops a bit because all those ions start crowding each other and dragging each other down. On the flip side, we have weak electrolytes like acetic acid. They only partially ionize, giving you moderate to low conductivity governed by Kohlrausch's law. And then you have non-electrolytes like a simple sugar solution, which produce practically zero ions, meaning negligible conductivity. All right, part 3, the non-aqueous challenge, conductivity in low polar liquids. We've talked about water, but what happens when we switch to non-aqueous solutions like toluene or hexane? The conductivity just absolutely plummets. I mean, we're talking incredibly tiny numbers, like 10 to the negative 10 Siemens per meter. Why the massive drop? Well, it's because the dielectric constant of these liquids is just so incredibly low. Their ability to store electrical energy and separate charges is basically nothing compared to water, which totally changes the rules of the game. Getting electricity to flow in these liquids is super difficult for 3 main reasons. First, simple salts just won't dissolve. You literally have to use amphiphilic substances, molecules with both water-loving and fat-loving parts, just to bridge the gap. Second, solvation happens through these things called inverse micelles. Basically, the molecules group together inside out to shield their core instead of forming normal hydration shells. And third, the positive and negative ions attract each other so intensely that if they get within a certain range, called the Jerem distance, they snap together to form neutral ion pairs. And since they're neutral, they absolutely cannot conduct electricity. Moving on to part 4, measuring conductivity, AC and DC. Because the real trick here is, how do we accurately measure these invisible ions with our lab apparatus without messing up their natural behavior? In the lab, we generally rely on 2 primary methods. For dilute solutions that have high resistance, we use alternating current, or AC methods, historically utilizing a Kohlrausch bridge. The AC method is super important here because it constantly flips the electric field back and forth. This stops ions from piling up at the electrodes, which is a major headache known as polarization. But if we're dealing with highly conductive solutions with low resistance, direct current methods using a 4-electrode cell are the way to go. They give us a nice, stable current measurement without all the messy interference you can get with AC. Next up is part 5, setting the gold standard, potassium chloride. To make sure any of these measurements are actually accurate across different environments, we have to calibrate our instruments. You can't just dunk a probe into a beaker and trust whatever number pops up. There's a very specific, step-by-step laboratory procedure you need to follow. Using your apparatus, like your clean beakers, measuring cylinders, and conductivity meter, you first calibrate the meter using a standard potassium chloride solution. Then you carefully rinse the probe with distilled water, immerse it right into your sample solution, wait for the reading to fully stabilize, and record the value. And of course, you have to rinse it thoroughly between every single test to prevent cross-contamination. Also, keeping your glassware spotless and avoiding air bubbles around the probe are absolutely crucial for getting precise results. And we have to be incredibly precise with that calibration standard. The NIST primary standard conductivity values for KCl are mapped out at very specific temperatures and concentrations. Notice that we use molality here, that's moles per kilogram of solvent, rather than molarity. We do that because it guarantees our concentration isn't artificially messed up by the thermal expansion of the liquid. Maintaining constant temperature control in the lab is absolutely paramount if you want a true assessment of your solution quality. Finally, Part 6, Modern Sensors and Applications. So, we've got the fundamental theory and the rigorous lab standards down. How does modern technology apply all this out in the real world? Well, we step way up from those basic lab probes to some seriously advanced commercial equipment. Take the Optex 6-electrode 4-pole sensor, for example. This thing is an engineering marvel. It actually uses 4 electrodes just to apply the current, and 2 entirely separate ones just to measure the resulting voltage. The electronics are integrated directly into the sensor, which pretty much eliminates any pesky cable resistance or capacitance. And the craziest part? With a 16-bit AD converter, it only needs a single calibration point to accurately measure a massive range, from 0 to 10 microsiemens per centimeter, all the way up to 850 millisiemens per centimeter. This kind of precision is a huge deal out in the field. Conductivity measurement isn't just a basic lab exercise. It's an essential analytical technique used everywhere. We're talking environmental monitoring, the pharmaceutical industry, food processing, agriculture, and wastewater treatment. It lets engineers seamlessly monitor industrial water quality and even predict how new battery electrolytes will perform without having to do endless, expensive trial-and-error experiments. Which leaves us with this pretty provocative thought. How can you estimate performance without embarking on a costly series of experiments? Well, it turns out that mastering this simple microscopic tug-of-war of ions is our most powerful and cost-effective tool for designing the complex energy storage of the future. Ultimately, a solution's conductivity really just comes down to the number and mobility of those ions. Thank you so much for joining me for this practical demonstration. Stay tuned for more explainer experiments presented by me, Dr. Chem, where theory meets real laboratory practice.